Our universe is filled with galaxies, nebula, stars, and planets, and perhaps most importantly, living things. But it's been argued that if the constants of nature were even slightly different, then none of this would be possible. And that this fine-tuning is evidence of a God that had to select the constants to be just right. The argument is often expressed like this: the fine-tuning is vastly improbable under naturalism, but not theism, and thus supports the existence of God. In this film, we'll hear from some of the world's leading physicists and philosophers of physics who'll explain why they disagree. We've had the good fortune to interview many of the world's leading cosmologists, and what's clear is there is far less consensus that fine-tuning is real than advocates of the argument let on.
I think it's a bit of a dangerous argument because we have no idea what life would be like, even with these numbers. We don't know enough about life to know that it would never necessarily come about with the numbers that we see. We don't know enough about it to say it wouldn't come about with other numbers. So I think it's a dangerous argument to use. There may be another reason why they have these values, which is purely mathematical. We just don't know. So there are big questions here, which are interesting to talk about, but I don't think you can make any big conclusion from them.
We certainly can't even go from the standard model to the periodic table of the elements, much less atoms and nuclei and complicated things that you need to make life. So what that means for fine-tuning is we just don't have a once and for all ability to say, with these laws, life would be possible, with these laws, it would not.
The argument that people have raised for many years about properties of water and properties of chemistry and nuclear states and carbon have all seemed a little bit unpersuasive to me because we don't know much about the details of life, really.
And people say, yes, but if the constants were a little bit different, there would be nothing. And that's incredible intellectual arrogance and stupidity, because nobody would be able today from the standard model to predict chemistry and life. Nobody at all. So how do you know what would happen if you change a value of of a constant? Imagine you change the mass of a quark, a coupling of the Higgs a little bit. Of course there would not be carbon, there would not be stars, but there would be something else. And nobody's able to say correctly and plausibly and credibly that the universe would not be complex and whatever, because we're not able to do this calculation.
One thing I've learned over the years working in philosophy is that you don't have to be convinced by an argument to be convinced that its conclusion is true. And in fact, I think it's very good to have an incredibly critical attitude towards arguments you feel are bad if you're passionate about the truth of the conclusion. So in my particular case, I look at the majesty of the universe. I look at the beauty, both the beauty of the manifest things around me, colors, flowers, animals, human beings, but then the beautiful intricacy of what we discover through science. And my immediate reaction is, I'm not inclined to believe this is all just an accident. I actually think in a way it destroys that entire driving feeling that actually I would say even drives me toward the scientific enterprise to say I'm going to take that transcendent thing and try to package it up and explain it away by some kind of argument. For me, it strikes me that that's the wrong direction here.
While Halvorsen does not seek to prove his theism with science, others have not been so cautious. Perhaps the most viewed take on the fine-tuning argument was presented by our friend Justin Brierley.
Now, what if I rolled this dice 70 times and every single time I got a 6? The chances of rolling a 6 70 times in a row are around 1 in 10 to the 55. That's a 1 with 55 zeros after it. Now, the odds of rolling 76s in a row, 1 in 10 to the 55, as it happens, those are the same odds of something called the expansion rate of the universe being just right for the existence of us here today. It hit 70 rolls of the number 6 in a row, first time. And the expansion rate of the universe is just one among 30 or so other incredibly sensitively finely tuned constants and fundamental forces in the universe that must be just the way they are for the universe to be able to produce us. The fact that we're here shows that someone's loaded the dice. In fact, maybe there's no dice at all. What if the evidence points to this life-permitting universe actually being the product of an intelligent mind?
So in the case of rolling dice, we're familiar, we've all had the experience of rolling dice. We know that there are different possible outcomes. And if we're not skilled cheaters, we know that when we roll the dice, the number 6 comes out approximately 1 time in 6. But we have no experience like that that is relevant to assessing the probability of the constants of nature falling, the constants of physics falling within some narrow range. We have never observed other universes where they take on different values. We haven't observed repeated trials of universes being created by the same processes to see what values the constants of nature take in those other cases. So we don't have any basis to assign a probability in the case of the constants of physics.
You roll a die, you know the probability distribution. If it's a fair die, you know it will be 1/1/6 of the time, 2/1/6 of the time, etc. In the case of cosmology or fundamental physics, that's exactly what we don't know. We don't know what that probability distribution is. So without that, all the analogies in the world are not helping us very much.
When people bring up the notion of fine-tuning, what they have in mind is they look at the world around them and they say, the universe around them, and they say, gee, it seems so unlikely. So the question is, what is the notion of unlikely that they're employing?
There's a few different ways you could try to say, that's what we mean when we say something's probable.
Most people nowadays will think that there are at least 2 different notions of probability. They're often called objective and subjective, but the objective one is something to do with what happens in the real world, and the subjective one is one to do with degrees of belief.
So I might believe different things to various degrees. I might be more confident that it will be sunny tomorrow in Los Angeles than that the Los Angeles Dodgers will win their baseball game.
The most common understanding of an objective probability is a frequentialist one.
We know, for example, that with human births, more boys are born than girls. So even though there are 2 possibilities and you might naturally think it's going to be 50-50, actually there's slightly more boys born than girls.
The other takes on probability, one was Karl Popper. He said a probability is actually a propensity in a thing. So a thing has this feature that it has certain tendencies. So you see there's sort of problems for all of these accounts of probability for pulling off a fine-tuning argument. Frequency, we don't get an infinite number of universes over and over again. At least most people don't think that. It's just one. We have one universe. So how could it be something that's probable or improbable according to long-term frequency? For subjective Bayesians, who cares what the probability is, because it actually it's not something in the world and it can't convince people. Because if they think this universe is likely, well, that's their opinion. And then propensity also runs into this problem that before the universe exists, it can't have a propensity to be one thing or another. So it does actually look like fine-tuning has slightly shady chances on any of the standard accounts of probability.
There are different cosmological theories about the origin of the universe, but none of them really posits a mechanism that can generate different universes with different possible values of those constants such that we understand the probabilities of getting those constants in falling within different ranges. So we don't have an analog of the roulette wheel.
In order to avoid these problems, fine-tuning advocates often appeal to something called the principle of indifference.
The principle of indifference says, in some sense, that if we're indifferent between 2 hypotheses, then we should assign the same probability to both of them. But there's many cases in which that's going to give us inconsistent results for the probability assignments that we make.
So, for example, 7 days in the week. You don't know what day it is. It could either be Monday or not Monday, and you've got no way of choosing between those 2 things. So the probability that it's Monday has probability half. So the probability of Tuesday is a half, the probability of Wednesday is a half, and so on. So applying the principle of indifference, you just get inconsistent results.
And things get worse for the constants of nature, as we could imagine them taking on literally any value.
Another problem with the principle of indifference is that when we're dealing with a case where there are infinitely many possibilities, there's no way of assigning equal probability to every one of the infinite possibilities. In order to do that, you have to introduce some mathematics called measure theory, and there are many, many measures which will give different results.
You need to assign a numerical value to each event representing the probability that it occurs. A measure is a mathematical notion. And basically, it's a way of assigning numbers to things.
Problem isn't one of defining a measure per se. The question is, what meaning could such a measure have? Could that correspond to anything that was physically meaningful or even psychologically meaningful?
There's not, to my mind, been anything resembling a convincing argument that we have the one true measure that anyone can say, this is the thing we should ask if we want to know, is our universe fine-tuned? We should be indifferent about them. And the only way to do that is assign them equal probabilities. That's all great and good. We're only cosmology that easy.
If you assign them all equal probability, if you give them any finite probability, they've got to add up to 1. And that can't, if you take any infinite number of finite quantities, they add up to something that's infinite. If you want to normalize and make sure you get a value that's between 0 and 1, you've got to say that each thing has 0 probability, but then we hit the problem of dividing by 0. But on the other hand, if you give them a probability greater than 0, then they're going to add up to something infinite. So, I mean, either it's 0 or it's infinite, and neither of those is going to work.
Ironically, two of the most significant critics of the fine-tuning argument who pointed this problem out are Lydia and Tim McGrew.
I think that actually was a quite brilliant move, and a move of incredibly high integrity, because Tim and Lydia McGrew, they're sort of well-known, theistic philosophers, to come in and say and in a way I actually say it was quite inspirational to me to see them enter into the debate with some of their peers and say, look, we're not against you in principle, but we don't like the argument you're pulling off right now. Let's raise the standards for the argument. So basically their main objection here is that, again, if you have infinitely many different possibilities, what you consider to be the right way of assigning probabilities to different possibilities is just not given in advance for these kinds of spaces. You're going to have to bring in some kind of contingent assumption, which actually just spoils the whole argument.
Rob Collins has suggested we ignore the infinite sea of possibilities and focus on what he calls the epistemically illuminated region, or the limited space where we can estimate whether the constants are life permitting.
I think Collins' argument is just a mistake. Maybe the right epistemic probability to have, once you see the dart hit it, is to think that the probability of the dart hits the illuminated region is 1, because you just seen it hit the region 1. Before it hit there, what should your epistemic probability be? Beats me. I don't think there's any particular epistemic probability to have.
Are we saying there's epistemic justification from physics that possibilities outside of this aren't relevant to the discussion? And if so, why? Or are we just talking about we, for some reason, are throwing away a bunch of the other possibilities? We're not taking those other possibilities, the ones outside the epistemically illuminated region, we're not taking them seriously. And my answer is, the more you make the argument subjective based on current knowledge, or whatever, the less force the argument has.
If we see somebody hit the bullseye repeatedly, we think, aha, they must be very good at darts. But again, if we knew nothing about this process, if we knew nothing about darts or dartboards, or the physical processes by which darts were sent to dartboards, we wouldn't be able to infer this.
A more unconventional suggestion is to simply give up on the idea that probabilities have to sum to 1.
We'll drop the requirement that if we sum a countable number, like the natural numbers 1, 2, 3, 4, if we sum all those possibilities, those will sum up to 1. We can drop that. That stops the objection in one sense. The McGrew objection has revenge, because the thing is, the best you can do in some sense is assign those events all 0 and still say there's something will happen, but they all have chance 0. Now, once again, the debate can go on, because clever defenders of fine-tuning, they might go to something like, we're going to go to infinitesimal numbers. Numbers smaller than any finite number are the chances of the different possibilities. At that stage, and I love mathematics as much as anyone, that's a stage where I say, this sounds to me like we've gone to Ptolemaic epicycles in effort to defend the argument. It feels to me that too much is being done to try to save.
Getting life-permitting values for the constants is often compared to winning the lottery. But with no bounds on what values the constants might take, this is an infinite lottery, and what are the odds of winning that? Mathematicians often distinguish between what is called the countably infinite and the even larger set, which is uncountably infinite.
It's even worse than the case of an infinite lottery if you get to something like a constant of nature. Because again, we tend to think these constants, we see no good reason to say they're restricted to a finite region. They could be anything. But now we have not just an infinite lottery, we have a lottery with uncountably many, infinitely, all the decimal numbers. It could be the constant could be that decimal. How do we choose what the more likely possibilities are? We have no rational a priori way to do that. It's not totally hopeless because we might hope that physics has a reason for choosing some measure over the other. In most of these cases, in many of these cases, there could be a measure. That is, there could be a way of saying this chance is more likely than that one and so on. But we're going to need physics to give it to us. We're going to need to have good reasons coming out of physics.
And indeed, in many cases, physics has shown us that what seemed to be extremely improbable ends up being extremely probable. Philosopher of physics Tim Maudlin illustrates this with a hypothetical skydiver, let's call him Phil, who seems to spend his entire life in free fall.
They're feeling wind all the time and so on, and they develop enough physics to figure out how much drag there is. And they realize at some point that the force of gravity downward is exactly and precisely balanced by the drag upward. So they're not accelerating, they're falling at a constant rate. And if you think about that balance, it looks wildly unlikely because the force of gravity is just given by how much mass they have, but the drag is given by how their hands are spread out and what they're wearing and all these little details of the air going by. So you might say, well, what are the chances that the downward and upward forces would exactly balance? And the answer is, well, they had to because they didn't when you started falling, and then you kept falling faster and faster and building up the drag until they balanced. So this is a case of homeostasis. This is where no matter where you started, you'll be out of balance at the beginning, but then the system itself will naturally go to balance and stay there. And so there's nothing miraculous about it, even though it would look miraculous if you just did the calculation.
We can't just calculate probabilities a priori. We need to have some understanding of the mechanism that produces outcomes or some kind of pattern of repeated trials that we can use to estimate a probability. So as an illustration, here's a jar and it contains both black beans and red lentils. It's kind of a vegetarian's delight with mixed legumes. So suppose I were to shake this randomly. What's the probability that all of the black beans would come out on top or would be in the top half of this layer of the jar? Well, we might try to compute that a priori. The probability that any one black bean will be in the top half of the jar is 1/2. And since there are 100 of them, the probability that all 100 of them will be in the top half would be 1/2 to the 100th. So this is an astronomically small number. So what happens when we shake this? What's going on? Well, we understand the process here. These beans are in a gravitational field. They're moving about, but there's a force that's trying to pull them downwards. And the little tiny red lentils are small, and they're able to kind of fall down through the nooks and crannies that the bigger black beans create. And so this process, it's random in the sense that it's not directed. There isn't an intelligent agency behind it. But it's a process that's taking place under a bias that is leading towards the red lentils to go to the bottom and the black beans to the top. And you have to understand the process to know that this outcome is in fact likely. It's in fact what you expect. And this number that you calculated a priori doesn't really have anything to do with what's going on inside that jar.
During the 18th, 19th centuries, astronomers noticed that all the planets travel in the same direction around the sun in an elliptical orbit, they're pretty much at the same plane. Given all the possible ways in which planets could travel around the sun in conformance with Newton's laws of gravity, this looks like very special. Why is it like that? And in fact, there were some philosophers, I think Immanuel Kant was one of them, who used this as an argument for the existence of God. Later, Laplace constructed a scientific explanation. He gave an account of the formation of the solar system, according to which is called the nebular hypothesis, which said that the sun formed out of a ball of gas, the rotating gas, and the planets were thrown out from the sun as the sun was rotating, and so naturally, since it's rotating in a particular way, they'd all be thrown out at the same angle, all traveling in the same direction.
Another case is the very example Justin gave in his dice video. It's also known as Dickey's flatness problem, as it's related to the fact that a flat universe, which allows the expansion rate to be just right, is unstable, like a pencil balancing on its tip. But the theory of exponential expansion, known as inflation, solves this.
Okay, just get inflation started and it will do all the heavy lifting for you. It'll make the universe really big. So it will make in particular, it'll make it very flat, because if you imagine like a curved thing and then expand it to be really, really huge, it looks locally flat, just like the Earth looks flat to us because we're real small compared to the Earth.
Inflation was originally thought to be driven by a phase transition known as supercooling. And as Alan Guth wrote in 1979, this kind of supercooling can explain why the universe today is so incredibly flat, and therefore resolve the fine-tuning paradox pointed out by Bob Dickey.
So the original flatness argument from Dickey was, if you start with a little bit of curvature of space in the early universe, it becomes more pronounced, more noticeable over time, unless you have inflation, which pins it back to zero curvature. But the question that we need to ask is, what is the probability that the universe would have started with a little bit of non-zero curvature? And again, we don't know the answer to that. Like, that's a very hard question to ask. But general relativity is our best theory of gravity and cosmology. It's a classical theory. There is something called the Liouville measure. There's a particular measure on the space of trajectories that you can calculate. And when Dickey did this, or when other people who do inflationary cosmology think about the flatness problem, they don't bother to actually ask what is the measure and therefore what is the probability. When you do, you find out that with probability 1, if you choose a universe randomly, it will be spatially flat.
The counterfactuals don't give you the probabilities. If I'm playing craps and I lose, I can say, if I'd rolled a 7, I would have won. That doesn't tell me anything about how likely or unlikely it is that of rolling a 7. So we can do the thought experiment and imagine a universe like ours with the same laws of physics and principles of physics, but with different values for those physical constants. That might tell us what would have happened in such a universe. It doesn't tell us whether those values of the constants were probable or improbable.
Cosmological constant is probably the best candidate we have for pointing at something and saying, here, we could imagine this being very, very different. If it were very large or very large and negative, there's just not enough time. There's just not enough ways to make a planet, much less a living being. That's very, very plausible. What we don't know is, how likely is it that the cosmological constant is big or small or anything like that? We can make a guess, and that's good, and we can make progress on the basis of that. Let's just not get too confident about it.
That presumption that the relevant quantity could take a big range of values is completely pure a priori. It has no basis in a scientific judgment.
There is a reason we call constants of nature constants of nature. Our theories as they are, they have some parameters in them that are constants. We can imagine other scenarios where their constants were different, but we don't really have a good theory of how that could happen or if that will happen. So that's really a matter of a speculation, and there's really no way of knowing.
If you think that there is fine-tuning for the constants of nature in our universe to allow for the existence of life, this is excellent evidence in favor of naturalism as opposed to theism. Because if you think about it, in theism, God can do whatever God wants. God is not constrained by the laws of physics. God does not need the laws of physics to allow certain physical configurations to exist in order for there to be life. God is infinitely powerful. God can do whatever. The only theory under which the physical conditions need to be exactly right to allow for complex chemical reactions in biology and life and so forth is naturalism. It's under naturalism that you need the constants to have the right values in order for life to exist. Under theism, life could exist under any conditions whatsoever.
Why does God need a whole universe there to bring life about? He certainly doesn't think that. He could just wrote about New York City. In fact, if I was God, that's what I would do. Who needs Los Angeles?
Fine-tuning arguments strike me as very unprincipled in where they're willing to have omnipotence play a role. So you could imagine, for example, a really wild scenario where like God just said, well, I don't need to go to any of this trouble to have there be assembled atoms and molecules and then biological systems, and why not just take something like electrons and endow them with consciousness? I mean, God can do that, right? As soon as you say God can't do that, I think the theistic arguer is in a very hazardous situation.
God's omnipotence, the very thing that allows us to assume he can change the constants of nature, is also the very thing that robs him of any motive to do so. In response to this line of reasoning, more sophisticated defenders of fine-tuning describe it as not for life, but rather the existence of embodied moral agents.
The claim has sometimes been made that in order for us to be able to commit morally significant actions, we need to have physical bodies. We need to be physically embodied. There are at least two reasons why I don't think that that claim is plausible. Presumably, if we were souls without physical bodies, we could still harm each other in ways that, in some spiritual realm. The other way in which I don't think that this is true is if we accept the Christian view that there are such things as angels and demons and so on, then those beings are capable of doing moral wrongs. So for instance, Satan was capable of rebelling against God and falling and so forth. And yet Satan is supposed to be a physically disembodied spirit. If Satan is a physically disembodied spirit and was capable of doing wrong, then apparently it's possible to do wrong without being physically embodied. There were theists historically who thought that it was a bad thing that we are physically embodied. So for instance, the Gnostics, the early Gnostic Christians, thought that the deity of the Old Testament was a separate demigod from the God of the New Testament that had sent Jesus. And that demigod from the Old Testament was the God that was responsible for our physical embodiment, but that the God in the New Testament is a God that we can come to only by overcoming our physical embodiment. If it's true that our physical embodiment was a bad thing, then it might be quite surprising that God would create us with physical bodies.
If the higher God never intended for a physical universe to be created, then having a landscape where creation would have hazard, creation could make something that's not intrinsically good, would be almost what you'd expect for the Gnostic God. Now this may be where it gets very exciting, because you say now maybe it would be almost like the problem of evil and the fine-tuning argument both could be right in some sense, because you'd say the lower God comes along and they're going to do something that's not at all the perfection, which would be to just leave nothing created. So it's going to both have the evil, but also it's a sign that there is this fine-tuning, because they at least wanted to get beings like us in the picture. So, I think there could be a very good case made that what you actually get upon consideration is something more like Gnosticism.
A key point to note then is that the fine-tuning argument can only get off the ground if we assume that the creation of the physical universe is something a good God would want to do. But what Gnosticism shows is that that doesn't follow from merely postulating God's existence.
If I flip a coin and it lands heads, I can think of a hypothesis that explains that perfectly, namely an all-powerful God who intended for the coin to land heads. I mean, that entails that the coin lands heads, because all-powerful God can't fail to realize his intentions. But this is rendering the whole process trivial. It's like firing an arrow at a tree and then drawing a target around wherever the arrow happened to land, because I could just as easily, I can always add a hypothesis like that following the discovery of anything. Say if I find that there's some trilobite at the bottom of the ocean that we weren't expecting to see, well, that's explained perfectly by an all-powerful God wanting exactly that trilobite to be exactly there, say, whatever. You can always just ad hoc add on these types of entailing hypotheses after any empirical data, whether it's about the hospitability of the universe or the way that a coin lands. What's going on here is a kind of abuse of probability theory rather than generally deriving probabilities and expectations based on hypotheses. It's constructing hypotheses to fit things we've already found.
I think the fine-tuning argument can sometimes backfire in a way that hasn't really been noticed by people who put it forward, and that is, if you take as an assumption, which I actually think is theologically very well motivated, that not only does God have a say in the game, if God exists, but that God has a say in setting up the rules of the game. So the way you can put that in terms of cosmology is, not only does God get to choose, in some sense, which of the universes comes about, but he actually has a say about which are more or less likely to come about. Imagine that you believe in some infinite being who designed some sort of game for you, and you believe also that this being, so I think in a paper I wrote some time ago, I actually called this being Gob. So G-O-B, just for fun. Now imagine that you, before you play the game, you think Gob really, really likes the color purple, right? So Gob really likes the color purple, hates the color yellow, wants you're gonna play this game where you're gonna draw a ball out of a hat, and you know this is the preference. Gob is averse to yellow, loves purple. Okay, so now you're going to play the game, but the game is to figure out who set up the game. Okay, so you're going to draw the balls out of the hat. Now, of course, naturally we think evidence for Gob's existence is you draw out a purple ball because Gob hates yellow, likes purple. Okay, so imagine now you're going to play the game. You reach down in, you pull out a ball, and it's purple. And you go, okay, I have a fine-tuning argument, right? Gob exists because I got a purple ball. That's evidence that Gob exists. Now, imagine you get round 2 of the game. Now you get to look inside the hat. Every ball but the one you pulled out was yellow. Every single one. Now what do you do? What's your feeling about Gob's existence? I think the obvious answer is it's a big defeater to the claim that Gob exists. But this is directly analogous to the fine-tuning argument because what we think is we got super lucky. We pulled out the universe analogy of a purple ball, a universe in which life exists. However, we look at the landscape of possible universes and it's an incredibly rare possibility. My reaction, which I think in that case is that's evidence against God's existence.
In other words, if God sets the probabilities for life and loves life, we should expect the probabilities for life to be high. Fine-tuning is the claim that the probabilities for life are low. Yet advocates of the argument, like Luke Barnes, claim that life would be likely given theism.
A lot of other things are likely, namely that if God is supposed to be the benevolent guy he's said to be, that it's likely that there wouldn't be a Holocaust, but we know that it's not true. So if we think of that as a hypothesis, as Luke Barnes was suggesting, it's been refuted not once, not twice, but 1 trillion times over.
I'd say, well, it's probable, it's pretty probable that there would be embodied physical organisms given that there's a God. And you might wonder, well, how do we know that that's probable? We don't have an independent way of establishing that. Shouldn't we be skeptical about that? Now, compare that to what they say about the problem of evil. Given the idea of an all-good, all-powerful God, you might think, yeah, it's really improbable that there would be such bad design, so many design flaws, and so much suffering in the world. And yet they want to say, oh no, you don't know enough about what is open to God, what God's intentions are, and what God's ways and means are, to rule out, or to sort of say that that would be improbable. Well, how do you get this knowledge? It seems like they help themselves to it in the one case when it helps their overall position, and say, oh, we don't have it when it would hurt their overall position. And that seems to be kind of arbitrary in a way.
The fine-tuning argument depends crucially on the assumption that God favors life-permitting universes. If you accept that, you very quickly run over to God would favor a universe without lots of suffering and things like that. So you're in jeopardy here. The extent to which you buy into fine-tuning, you're going to run into the problem of evil.
If there's a designer, what's the designer interested in designing? Now, if you say life, why life? Because I'm alive? Why, oh, human beings. The designer really wanted human beings. Went through all these millions of years of dinosaurs to get there? That doesn't make any sense, right? That's just egocentrism. We put ourselves at the center of the thing that needs to be explained.
One way of motivating the idea that God has some specific intentions is to say that God is like good, or something like that. But then why think that God is good? Well, one classic way that people have done that is to appeal to, say, an ontological argument, which is trying to show that God is a perfect being, right? But if you've already got an argument that establishes that God is a perfect being and therefore exists, you don't need to run the fine-tuning argument, which doesn't actually entail that God exists, it just raises your expectation that God exists. So why bother with the fine-tuning argument if you've already got a deductive argument that proves that God exists? There's no point to it. If you need a stronger argument to support a weaker one, the weaker one is redundant.
Many theologians suggest the universe could not produce life by purely natural means, but it's hard to see how this can be squared with the claims that it's also fine-tuned for life. After all, we wouldn't suggest that an object is perfectly designed for flight if it needs a miracle to get off the ground.
That there is no adequate theory, not even a shadow of a theory that would explain the origin of life on this planet, and that the evidence is quite consistent with thinking that the origin of life required some sort of miraculous intervention by God.
On the one hand, we can see cases where nature is designed well, you know, and we say that must be a sign that God did it. On the other hand, we see cases where nature is insufficient, and we might be tempted to say, so God had to do it, God had to breach the gap. They want the parameters and so on to be set up so that by itself nature would lead to life. So it's almost like they're saying there can't be we're going to ignore the fact that we traditionally have put a miracle here. Now we need a miracle earlier, namely the miracle that we got the constants that permit life. It feels to me like we're playing a non-principled game here.
To think that we have empirical evidence that the constants of nature are the kind of thing that we would expect to be the product of intelligence, we have no evidence for that. We just have never seen anything like that produced by intelligence.
The German metaphysician Leibniz, he actually said a miracle would be evidence against God's existence, because God would design a universe that was so perfect it wouldn't need miracles.
Another way to formulate the argument is to suggest that the fine-tuning is due to necessity, chance, or design, and then try to rule out the first two options.
The most promising candidate for a theory of everything to date, superstring theory, or M theory, allows a cosmic landscape of around 10 to the 500th power different universes governed by the present laws of nature, so that it does nothing to render the observed values of the constants and quantities physically necessary.
We certainly can't say string theory predicts something and therefore it's true. We don't know whether string theory is true. We don't know what string theory predicts. These are the two major problems there. So when it comes to what string theory predicts, I think we should take it very seriously. It seems to predict there's a landscape of different possibilities, but there's plenty of string theorists out there who doubt that, and they're trying to understand that, and it's very hard to do.
String theory is really a speculation about the nature of quantum gravity. Even though it's the leading proposal, it hasn't really been tested in any way.
If string theory itself cannot explain through necessity the values of the fine constants, then maybe so much the worse for that avenue in solving the fine-tuning problem. Perhaps it can. Perhaps there'll be another theory that will prove better than string theory. So all of these questions are entirely open, and therefore we cannot rule out necessity.
So if it can be shown that it's necessary that the constants of nature take the values that they do, then I can imagine somebody saying, well, then why did they take those values? Isn't that itself a sign of intelligent design? I think that's a different argument, because that's not trading on the improbability of the constants taking on a certain value.
Now, you could come up with some speculative other theory. Maybe there's an infinite number of universes, giving you an infinite number of chances to roll the dice. Maybe. But we don't have any scientific evidence for it. So if you're hanging your hat on that possibility, then you're every bit as much committed to a faith position as the person who says God was behind it.
Comparing the multiverse to God is not really a fair fight in terms of thinking about hypotheses and theories to explain the universe, because the multiverse, as unclear and uncertain as it is, we have no direct evidence that it's out there, it's a scientific hypothesis. We have equations that tell you what happens.
Speak to the multiverse problem, Dr. Lennox.
My instinctive reaction is it is the biggest violation of the principle of Occam's razor we've ever seen. In other words, that principle that we normally use in science and in our investigation, that we keep the number of hypotheses as small as possible.
The point that a lot of skeptics about the multiverse don't understand is that you don't postulate a multiverse. That's not what you do. That's just a mistake. They're getting it wrong. What you postulate are laws of physics that give rise to a multiverse. It would be like complaining that there are too many integers. You have 0 and 1 and 2, and there's an infinite number of them. That's crazy talk. That misunderstands what the integers are. You start with 0, and then you have a rule for making more. Within physics and cosmology, that's where the multiverse comes from.
There's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved.
Okay, if that solution is no good for you because it can't be tested, then the problem shouldn't be any good for you. Oh, very good. That's very good. That's very good. I agree fully. We cannot test the idea that changing the fundamental parameters you don't have life.
We're going to call foul at speculation for a multiverse theory. I think I'm going to call foul at speculation about what occurs with small changes in the constants or with changes in the constant of nature.
Multiverse hypothesis is relatively new, and really what it is a response to the fact that the universe appears to be so designed. Nobody would be thinking that there are other universes out there unless they realize, wow, this place is so designed, we've got to multiply our chances that this could have happened without intelligence if we're going to say there's no God.
This claim is simply false. While the multiverse is still controversial, and we'll hear from both supporters and detractors, it was not invented to deal with a theological fine-tuning argument, but it seems to arise naturally from inflationary cosmology.
Once inflation starts, it just never stops. And the way that works is actually fairly simple. Inflation is driven by a kind of gravitational repulsion, which is in turn created by a certain peculiar state of matter. And this peculiar state of matter that creates gravitational repulsion is unstable. So it decays pretty much like a radioactive substance decays, just randomly, without any way of really predicting when it will suddenly start to decay. And this decay starts locally, as a small patch. So if you wait for one half-life of this decay, then really by definition, half of the space that you were looking at that was inflating will no longer be inflating. But the catch is that the exponential expansion goes on all the time. So for the parameters that are appropriate for most versions of the theory, during the half-life of the decay, the region that has not decayed has expanded by a factor much, much larger than a factor of 2. So at the end of the period, you end up with more space inflating than what you started with, even while it's decaying. And this goes on forever. Whenever a decay takes place, that really creates a local Big Bang. It creates a local universe, which we sometimes call a pocket universe in this context to distinguish it from everything. And these pocket universes go on being created in the context of these theories ad infinitum.
Following NASA's CMB probe WMAP, declaring they had detected a key signature of inflation, ESA launched an even more advanced follow-up mission called Planck. George Eustathiou was the cosmologist chosen to present its cosmology results.
You know, the simplest models would have an eternally inflating universe.
And Planck favours those models.
Yeah.
So when I hear all the time on TV there's no evidence for a multiverse, what you're telling me seems to imply there is.
Yep, and if inflation is eternal, then you have a multiverse. And that's why I say that, you know, I think this is the most important result from Planck. We're sort of being pushed towards, you know, now experimentally in the direction of a multiverse.
In our visible universe, we think that life does not arise uniformly in all places, but life only arises in very special places. And there's every reason to think that in the multiverse it would be the same way. Most living things would see laws of physics, low energy, local laws of physics that would be conducive to life. And it would not be because the laws of physics are actually fine-tuned, but just that life only forms in those particular kinds of vacuum which are suitable for the creation of life.
In the 1980s, Nobel Prize winner Steven Weinberg used the idea of a self-selection effect in a multiverse, otherwise known as anthropic reasoning, to predict a small value for the cosmological constant.
It came as a shock to most physicists when the anthropically predicted value of the cosmological constant was actually observed. And this changed many minds.
I do think that Weinberg's prediction, really, of a value of the cosmological constant, which is non-zero but close to zero, was extremely striking. I think it greatly impressed the community and made us all believe that, gosh, there's something to anthropic reasoning and it might really deliver.
While inflation is the mainstream view of cosmologists, it is not without its critics, who propose alternatives which we've documented in our film series Before the Big Bang. Many of these critics deny that fine-tuning is real. Others suggest that alternative schemes can also give rise to an ensemble of universes.
Well, CCC is a different picture. It's a sequential. You say there are different eons, one after the other, but not next to each other in this other sense. And one possibility might be that in the eons of CCC, these numbers have different values. And there's this thing called the anthropic principle, which might say, well, we're only in that eon where these numbers have exactly the right values, where life could come about, and if you changed monkey with these numbers too much, life wouldn't happen.
Given this, our friend Justin Brierley, author of the infamous DICE video, invited Phil and the Christian apologist and physicist Jeff Zweerink onto his podcast, Unbelievable.
I'm ready to hold my hands up, guys, and say if I jumped the gun, as I think probably it would be fair to say lots of other people involved in Christian apologetics, by saying there's no scientific evidence for a multiverse in that video, then I'll hold my hands up and say, my bad.
If this is true, I may just have to say that we don't have a fine-tuning argument right now. And so I think that is something as Christians we need to wrestle with pretty seriously.
One criticism of the multiverse is that
The universe generator itself would require an enormous amount of fine-tuning.
exactly what justifies this is not clear, but it may be related to the claim that inflation is unlikely to start in the first place.
There has been some debate in the physics literature about how probable it is for inflation to start. My point of view really is that that discussion is pretty much just irrelevant if inflation has a high probability of becoming eternal, because eternal gives you an infinite factor for the space-time volume that comes out of inflation, and infinity is a large number, and I think that makes it pretty much irrelevant how likely inflation was to start, as long as you think that there's some non-zero probability of it starting. For the people who do play that game, people reach different conclusions because in truth we don't have any theory of the actual creation of the universe. So people make different guesses and come up with all kinds of answers. Some saying inflation is very likely and some saying inflation is highly improbable.
The main argument against multiverse hypotheses that are being floated today in cosmological discussions. And the idea is this. It is far more likely that a single brain would fluctuate into existence out of the vacuum than that a universe finely tuned like this at a low entropy condition would come to exist.
You would get Boltzmann brains even if there was no multiverse at all. The idea is you just wait long enough. You don't change the constants of nature or anything like that. You just have a soup of these individual molecules floating around in space, and you give them an infinite amount of time and only a finite amount of space, and they'll eventually bang into each other the right way to form pretty much any structure you want. This has nothing to do with the multiverse at all. It's an entirely orthogonal question.
One way out of it is certainly to accept the notion of a multiverse, that our universe is not the only one, but one of many pocket universes. And then the Boltzmann brains in our universe can be outnumbered by normal life in parallel universes. And for many kinds of measures, the Boltzmann brain problem can be solved.
The Boltzmann brain problem is weird in how people have sort of latched onto it. It's a very specific problem. If a very specific set of things happen, namely the universe lasts forever, and as it's lasting forever, there are random thermal fluctuations within it, then we should get Boltzmann brains and we should have a very different universe than what we see. But neither one of those assumptions are automatic, even if you believe in a multiverse. Maybe it's a finite amount of time, but much more likely, the way the multiverse exists and evolves over time is just completely different than random thermal fluctuations. That's a very easy thing to set up. So the Boltzmann brain problem is not a statement that the multiverse is in trouble because there are too many Boltzmann brains. It's just a statement that you should avoid those particular versions of the multiverse which are dominated by Boltzmann brains. That's not that hard to do. It's not a big problem. Get over it.
As Roger Penrose has pointed out, while multiverse or anthropic reasoning might address the fine-tuning of the constants, it can't resolve the apparent low entropy at the beginning of the universe.
I'm of the belief that the fact that our early universe had low entropy is a huge problem for modern cosmology. Problem in the sense of a puzzle we need to solve. Not that it's unsolvable, it's extremely solvable. I have suggested solutions for it with my colleague Jennifer Chen. We proposed a multiverse model which would explain why our early universe had low entropy. But the anthropic principle does not by itself solve it. With that, I agree with Roger Penrose, because the early universe's low entropy is much, much lower than it needs to be to allow for the existence of life. So I would take that as a strike against those who want to explain fine-tuning using God, because here's an example of a fine-tuning that was not just for us to exist, right? It was clearly some dynamical mechanism that has nothing to do with the existence of life, yet we have some fine-tuning to be explained. It could very well be that other fine-tunings have similar dynamical explanations.
Pretty gross coarse tuning. The entropy in the gravitational field is ridiculously small compared with the entropy in matter. There's nothing fine-tuned about it, it's just huge.
What you were saying was,
yes.
People had argued there are these constants that's fine-tuned for life, and he said, well, hang on, look at the entropy, that could be much, much higher, and life would still be here, so that's not fine-tuned for life. Therefore, we see something that clearly isn't.
I absolutely
Would you agree with that?
I absolutely agree with that, yes. That's something I agree with.
Sean Carroll has constructed a model which adds more to the universe, which explains how it is that our universe would have formed with very small entropy. And Roger Penrose has constructed a different model based on his unconformal geometry and black holes. And there may be other ideas around.
And indeed, loop quantum cosmology and the Big Bounce suggests another potential resolution that has nothing to do with light.
In the quadratic branch, because the dynamics is different from Einstein's theory, a horizon develops, but it grows extremely rapidly. And in fact, therefore, the entropy really grows extremely rapidly. And as usual with black hole horizons, this entropy dominates completely the entropy of matter. Therefore, the entropy is really growing very rapidly, but then at the bounce, the geometry is such, which is non-trivial statement, is such that in fact the area of this horizon becomes infinite. And then after that, the horizon simply disappears. So if you like, what one has to do is to reset the entropy clock in a certain sense at the bounce.
If fine-tuning is real, then it suggests the constants of nature were not chosen randomly and only once. But there's nothing in naturalism that says that has to be how the constants were selected. One of the critics of anthropic reasoning is Lee Smolin, who's developed a model of cosmology known as cosmological natural selection, where the constants of nature are forced into a life-permitting range.
Lee Smolin, several times in his career, has introduced ideas that amazingly address or even solve problems that no one's had any inkling how to do it. Not that he's right in his solutions, but it's a possible solution. And for that, I give him great credit. And the case of cosmological selection, I think, is an example. It's a way of solving fine-tuning problems, but without introducing an observer selection effect.
I saw this as a problem akin to the problem of biology, which is to explain why the different creatures in the living world are so fit. If you imagine that the parameters of the standard model are like the genes, then with different choices of the genes, you get different organisms in different ecosystems with different populations of organisms. the animals or the organisms are fitter than they would be under a random change. This seems analogous to the claim that the universe is more complex and more hospitable to life for the present values of the parameters than for random values of the parameters. So I wondered whether there could be an explanation akin to biological natural selection, which would apply at the scale of the universe as a whole.
Cosmological natural selection offers the idea that a new universe comes into being at a singularity of a black hole. Each universe is equipped with a set of parameters, the parameters of nature, that govern the physics in that universe. And the parameters change a little bit between the parent universe and the new universe. There is a set of parameters, it is postulated, that maximizes the number of black holes formed in a universe, in a given universe, and therefore maximizes the number of progeny that it produces.
If you have a biology of this type for universes, then you could then apply the theory of evolution to the universes and ask, okay, so what is the fittest kind of universe that you could have? And if you just follow very naively the same thing that you do in evolution, basically the fittest life form is the one who can have most offsprings. So which is the universe could make most black holes, right? So that was his idea, that basically you're not really fine-tuning for life, but you're really fine-tuning for more and more black holes.
Although Steven Weinberg predicted the value of the cosmological constant using anthropics, Raphael Sorkin also made the same successful prediction on the basis of his theory of quantum gravity, known as causal set theory, which posits that there are atoms of space and time. Recently, it's been suggested there's a link between causal sets and cosmological natural selection.
Dauka and I studied whether cosmological natural selection could be compatible with causal sets theory. The singularity is what separates the mother universe from the progeny. Once we defined those structures, we studied the dynamics of causal sets around them. So the dynamics in causal set theory is given by a set of parameters, which in this model play the role of the parameters of nature. And we've shown that there is a process of change. You can repackage the parameters in a different way on each side of the partition or in each universe. And so this idea of changing of the parameters of nature across the singularity was echoed in those ideas.
Lee Smolin also claims that his model makes predictions for astrophysical data.
The prediction is that universe picks constants such that the maximum mass of neutron stars is the smallest possible. So Lee's suggestion was that it cannot, so the maximum mass cannot be bigger than 2 solar masses. We've now observed neutron stars that are just as massive as that. So he's kind of on the verge of that prediction being ruled out possibly. But then really the question is how sharply you can put that value, because there's a lot of uncertainties, and the real uncertainty is what is the type of the nuclear matters that you could have. So there's the main uncertainty, in fact, in this game is that what's known as the nuclear equation of a state, and the maximum mass could vary by 100% basically, depending on what choice you make. And then the other question is that could there be different types of neutron stars with different equations of a state? So if you detect a neutron star with, I don't know, 2.5 solar masses, does it mean that that's the maximum for all the neutron stars? Or there could be different types of neutron stars, that some of them are much more susceptible to form a black hole. So we don't really know. That's the uncertainty here.
The difficulty with raising God as explanans, we philosophers, we have the explanandum, the thing we're going to explain, and we have the explanans. If God is the explanans on the basis of intent to bring about what is otherwise seems enormously improbable, then we have an explanation for absolutely everything that we might be baffled by. A sort of a universal explanans for an endless explananda without end. This is part of the reason why I think it is a bankrupt policy to appeal to God at the level of detail. If we do that, we are really infantilizing ourselves. It's contrary to our entire experience after 2,500 years of science. This isn't how we make progress. This isn't how we deepen our understanding, and it isn't how we give genuine explanations.
For fine-tuning, it's not clear that there's a problem to solve. And if there is, there's no shortage of solutions, none of which have been ruled out. The constants might be set by necessity or by chance in a multiverse, or they may be selected via a Darwinian process, or perhaps some other mechanism yet to be discovered. And at the moment, we can't say which of these are true. But that gives no justification for accepting the conclusion of the fine-tuning argument.